I hope you can see the slides. I hope you can see the slides.
Yes, sir.
Okay. Now, last day we had stopped somewhere here, isn't it? So just recapping things. But I said that even if you're in equilibrium, you have fluctuations in equilibrium. For example, you simulate something on a computer in an ensemble like NPT ensemble, for example. You can simulate, or NVT exam ensemble, doesn't matter. But you will see if you simulate the system in NVT ensemble or NPT ensemble, the energy, internal energy of the system is not constant. It is fluctuating. So actually you can calculate what is known as the variance. Okay, you know this is called variance, sigma is square. And a square root of this is called, what is that called? Square root of variance?
Standard deviation.
Standard deviation. So the standard deviation in energy you can always calculate. You can calculate E average, you can calculate E square average, which we did in the last class. And it showed that, go to the next slide. For example, this is a typical snapshot of a system. This is energy as a function of time. I should have put time there. So let me put it. So basically what you have here is yeah. So what you have here is some energy. The internal energy as a function of time. And it will fluctuate some kind of time. So in simulation, you can take a time average, for example, but you know time average is equal to ensemble average. Okay. So Anita Puri is why. Hey Anita, you have to use LDAP. Anita, you have to use LDAP in order to entry. You're not using LDAP. Anyways. Okay. So not this one. I have, yeah, this is the one. So so this quantity, this CV is called heat capacity at constant volume, isn't it? And this is related to some kind of fluctuation which you are in equilibrium, but equilibrium fluctuation. So this is also, in general, this is a response function. Obviously, I can think of another response function, which is this, CP. Heat capacity at constant pressure. This you calculate in NVT ensemble. This you should calculate in which ensemble?
NPT.
Yeah, you can calculate in NPT. So this one you will calculate in NPT. And how you are going to do it? Not very difficult. For example, in NPT ensemble, I can define a partition function. And this is going to be sum over J and volume actually. And this is exponential of minus beta. Okay, you take it for granted because you did not do. This is how it looks like. The partition function is NPT ensemble. Okay, so let me go to this slide. So what I have here is this partition function. In entropy ensemble is given by J V. Of course, this one is a function of N, P, and T. P is pressure. So how do you then calculate, for example, if I want to calculate the average energy in NPT ensemble, you know how to calculate, no? It has to be, sorry. If I write anything wrong, please let me know. This is fine. This is average energy. Okay. Now, if I take this average internal energy, I differentiate this guy with respect to beta. What I'm going to get? Can you differentiate this function, this expression with respect to beta? All of you. You remember the formula, no? All of you? Differentiation? Say yes. You don't remember or what? Nashid?
Yes, I remember.
Yeah. So just give me, I'll tell you how. So if I have a function of x, and if I have a divide by function of another function of x, and I take ddx of this, what should be on your right hand side? Tell me. Gx square. What should the first term?
Sir, f dash would be,
Tell me.
sir, f dash x into gx minus
Minus.
g dash x into f of x.
This is how it is, isn't it? Just you check this derivative rule is here. If it is f by g, then f prime g minus g prime f. So exactly what you did. Okay. Now, if I do this, what I'm going to get? The denominator is going to be whole square. Fine. What is the first term? Hey, please mute yourself. What is the first term? F prime x. F is the numerator, no? So I have to take a derivative of this with respect to beta. So if I take a derivative of this with respect to beta, what I'm going to get? I had ej, but beta means this function will be there, but ej plus pv will come down, no? Come down, isn't it? Is this clear?
Yes, sir.
But anyway, I have done a mistake because I should not calculate average internal energy, rather I calculate average enthalpy here. That is more appropriate. So I should calculate average enthalpy. And this is going to be ej plus pv into this, isn't it? Average enthalpy you should calculate in this case. So let me write down again because it is looking very clumsy. So I should have okay. So what is the first term then? First term is, this is your f, no, the numerator. So first term has to be f prime. So derivative of f with respect to beta. So this is minus, huh? So it's obvious that what I'm going to get, I'm going to get minus ej plus pv, but you have two ej plus pv, one is already there, you square of that. What will be the next term? Minus sum over j and v, and then tell me what is g prime x? This is g, no? This has to be
minus EJ plus PV
plus pv exponential of
into
minus,
exponential of minus beta EJ plus PV.
but then you have to have another term, isn't it?
Yeah,
What is
numerator.
that?
The numerator term.
Yes, here also you should have it. You should have it, no? I forgot to put this. Here you should also have jv into hope this is fine with you. Now what is the first term? If I write it very carefully, what I have here is, see, look at it, this is a separate term, no? Let me write it cleanly. Okay, this is, there's a minus here. Okay, the first term is going to be this, and this will partially cancel, no? This is the denominator is the square of this. The first term will give you minus jv the whole divided by what is this? What is this term?
Average enthalpy. No,
Look
no,
at
no,
very carefully.
no, no.
Enthalpy is this.
And
That is your enthalpy, no? So this is actually, this is minus of enthalpy square average, isn't it? Is it fine?
yes, sir. Yes, sir.
Yeah. What will the next term? Next term is, you have minus minus plus, of course, plus, and then you have two terms are identical actually in the numerator. So I can take a square of it divided by square of it and what is this term?
Average enthalpy square.
Yeah, because actually this is, if you don't like it this way, I can write this way. I can take whole square. And what is this? As you told, this term is nothing but it is h average and then square. Of course, you have plus term. So what you get here is your, let me write down here, You get daily average by del beta.
So del H average.
Yes, sorry. Yeah, it should be del H average. This is a typo. So del H average by del beta is now you know beta is 1 over kVt. So del beta is, you know what is del beta? Is it fine? So it basically
Yes.
tells you and what is this? This is, isn't it? Fine? Is it fine if I write like this?
Yes,
And
sir.
what is this quantity?
So
You know very well.
at constant pressure it is
Yeah, it is
V
actually
and
Cp.
the CP. Yeah.
So basically it tells you that, okay, kBt square Cp is equal to sigma h square. You can check the previous relation. You had this. In the previous relation you had, if you go back, you will see that kBt square into Cv is equal to sigma e square. You had this, no? So now you also have the relation of heat capacity at constant pressure with sigma h. Okay, you have it. Anything else you can calculate in this ensemble? For example, I can calculate average volume. I should be able to calculate average volume in this ensemble, no? What is the definition of average volume? This has to be JV V exponential of minus beta okay. Now if I take a derivative of this with respect to pressure, what I am going to get in the right hand side? Same rule, no? JV whole square. The first term is the derivative of the numerator with respect to P. What I'm going to get? Someone can tell. V, then I differentiate this exponential with respect to P. What I'm going to get? I'm going to get minus
beta V.
beta
Beta V.
into V. Okay, but you also have the second term. What is the next term? Now I have to differentiate this guy with respect to P. This will be into minus beta V. Is this clear? Of course, I have this. What I can take common here is minus beta, no? Minus beta is common, okay? Now what is the first term? First term is V square This is your first term. If I do any mistake, please let me know. Your first term?
Yes,
This is your
sir.
first term. Tell me.
Yes, sir.
And what is the next term? Next term is going to be again the same. Whole square to v, I think we put it here, whole square so what is this then? Minus beta. First time, you know, I'm not going to write it again. It is v square average, and the next
Minus
one
V
is
average.
here square. Okay, is this fine?
Yes, sir.
And there is something called isothermal compressibility, which is defined like this for a material. Which is kappa is minus 1 by v del v del p at constant t. And if I follow all this will give me kappa is equal to sigma v square by v into kVt. So this is another response function. Okay, but you should see that, okay, what happens that higher the fluctuation, higher this standard deviation, higher the value of this. What happens when a material is undergoing a phase transition from liquid to solid or say gas to liquid? At the critical point, these fluctuations become huge. Okay, and then it goes from one phase to the other phase, because there will be sharp change in isothermal compressibility, heat capacity, you understand? So these are signature of phase transition. You actually follow these quantities in order to quantify phase transition. I don't think we'll have time to discuss phase transition in detail in this course, but if you take a course in physics, statistical physics, two kind of course in physics department, I think they are going to discuss phase transition in details using StatMech. It's very, very important. Okay. So after this, we move to today. Today we'll move to some new topic. So this, the part so far I've taught today, discussed today, you can read it from the book by Professor Biman Bakshi, chapter 6, also from the book by McCurry, Statistical Mechanics book by McCurry. Okay. So now after that, we just move back to our old canonical ensemble, and then I consider so I'm in canonical ensemble. I'm in canonical ensemble, and I have a system made of one particle, single particle essentially. And this particle is structureless. So if I have n such particles, structural is like a point particle, okay, like a dot. And if these particles are non-interacting, and I can put in a volume, total volume V, temperature T, then I'll have an ensemble like NVT, isn't it? And this collection of n such non-interacting particles, structureless particle, you know what is this called? If you have n particle, they have no structure. I mean, these particles have no volume, and they don't interact with each other. What is that called? This collection. Everybody knows.
Ideal monatomic gas?
This is nothing but ideal monatomic gas. Okay. If the gas is not ideal, then these particles will have some finite volume, like van der Waals gas, and also they'll have some interactions between them, isn't it? So essentially what I'm doing ideal monatomic gas system. But before I get into the system, let us consider only one particle. If I consider only one particle, of course, the point particle, it cannot vibrate. There's no vibration, there is no rotation, nothing. What it can have? It can have only translational motion. So only translational motion. This is clear, I'm sure.
Yes, sir.
Okay, so let us now calculate the translational partition function for the single particle I'm doing. For the single particle, this is Q trans. I'll ask what is this. For the total partition function, if it is for this system, n number of particles, okay, I can think that, okay, the single partition function is given by exponential of minus beta ej and some overall possible values of j. And if these particles are non-interacting, and if the particles are distinguishable, so that I can tag them A, B, C, D. I can tag them A, B, C, D. I can color them different color. Then what is going to happen that I have something like j exponential of minus beta eaj into j exponential of minus beta ebj. These are particle index, ab. I have n such terms. So in other words, but again, these are again dummy variables. I'm saying a, b, c. No. So each of these sum, after doing summation, they'll give me identical results. So I can say actually this partition function is given by q trans for A times q trans for B dot dot dot, and I can say if all the particles have same mass, then I can say this is like this. But this is true only when the particles are distinguishable, non-interacting but distinguishable. We will see later what happens if the particles are indistinguishable, which you'll see later. Okay. So now let us come back to this Q translation. How to calculate? Any suggestion? Any suggestion from the students? Well, how can I calculate this translational partition function?
We probably have to integrate over energy, right?
Yes.
Because
So basically, I can assume that, okay, I have a box of a cubic box of length L. And in that box, I have the particle. I have a single particle, of course, structureless. Okay. Now I go back to quantum mechanics. People who has not done quantum mechanics, just recap. I can think that the particle follows quantum mechanics, and then I can calculate the energy of that particle in particular state. You see that if you have a cubic box, and you cannot cubic box, the length is very large, for example. Then I can define this box with quantum numbers ny, nx, and nz in 3 directions. So this is your x direction, this is your y direction, this is your z direction, c direction. And this expression, I think you remember. How many of you remember? This is essentially particle in 3D box.
nx square plus ny square plus nz square.
Yes. This
Time
is
resist.
going to be nx square plus ny square plus nz square. L square actually. Sorry for this. I think you know m is the mass of the particle. Huh? So ideally, your translational partition function should be sum over this nx, ny, nz exponential of minus beta into nx square plus ny square plus nz square Of course, you remember that nx, ny, nz, they vary from 1 to infinity in unity. Okay. The they're not fractions, of course. So this one, in the next step, I can say these are like dummy variable, no? Nx, ny, nz. So I can always split this into, and you know that your exponential of a, b, c is exponential of a into exponential of b into exponential of c anyway. Huh? So I can split this into 3, isn't it? Into one more, same thing, one more, same thing. So I hope you follow what I'm doing. I'll do it again in the next slide. So what I have here is nx and this one is nothing but, because these are like dummy variables, I can always write this is something like this is minus n square h square beta Is this clear? Because each
Yes,
sum is identical. Now this sum is, rather I approximate this sum as an integral, okay? And I allow my n to go from 0 to infinity. Although n cannot be 0 strictly, but this is an approximation. Because this function, if you plot this function of n as a function of n, this will be something like this. Each term will add. Okay, and the this integration will be something like this. So not a bad approximation, you can go and check. Okay, so essentially what I have an integration of this which is equal to, let me write down it very cleanly. Okay, this is fine.
yes, sir.
Now again recall Gaussian integral. You remember this? What is the answer?
Put pi by alpha.
Yes. So basically, but the integration limit is from 0, so it has to be half of whatever I can say, na? So what is the answer? This is half pi by alpha, no? Pi, what is alpha? I am doing it in very detail because it is important that you do once. What is this? This is alpha?
Yes, sir.
So let us do it. Let's do it and put it. It is going to be pi by h square, of course. This will be 8 ml square kb t. Okay. Now I forgot to say till this because you have a whole cube, isn't it? There are 3 terms. Remember?
Yes, sir.
This is for one term, no? So basically you should have a cube of this. So that will give you your translational partition function for a single particle. So what is the answer then? Can you just simplify this?
Yes, I think it comes to
Yeah.
2 pi ml square kbt.
Yeah. I'll tell you. It is not very difficult. What you have here, it is 1 over 8 into 8 to the power 3 by 2. This is fine.
Yes, sir.
And then L square and half will cancel. You'll have L cube. And then you have pi is there. So pi m kbt divided by h square whole to the power 3 by 2. This is what you have, no? And this will give me what? L cube is something like volume. But this is not the big volume. This is the volume of a single particle. Okay.
Yes, sir.
Now, volume of a single particle is what? Is the volume of the box, essentially, in this case. Because it is volume available for the single particle, that is the right statement, isn't it? L cube is the volume of the box, isn't it? The cubic box.
Yes, sir.
So this is L cube, volume of the cubic box, or volume available for this single particle, because the particle has no volume. And you know this 8 3 by 2 by 8, which basically means what? 8 3 by 2 by 8. What does it mean? 8 3 by 2 by 8 means 8 half, isn't it? 8 half.
Yes, sir.
So 8 half is, 8 to the power half is 2 into 2 into 3 half, which is equal to
2 into 2 into 2 power.
sorry, 2 into 22, which is equal to 2 root 2, isn't it? It has to
Yes,
be 2
sir.
root 2. So which is 2 to the power of 3 by 2. Huh?
Yes, sir.
And then what you have is a twice pi m kbt by h square 3 by 2 into v, and this is your translational partition function. I hope this is clear because I have done everything in very detail. Okay. If this is translational partition function, then heat capacity per particle, of course, something like that. For your system is made of one particle, say, whatever. What is his heat capacity? It will be, you remember the expression? What is the expression of heat capacity? It
Delhi
is,
delta
but again, you know what is E average? E average is,
KBT square d log QDT.
let us do it for single particle flux first. What is this going to be? See, this is ddt of, if I write it very carefully, this, you have some temperature dependent part and then other parts are temperature independent, isn't it? So actually you have ln to the power of 3/2 plus some other terms which are independent of temperature, isn't it?
Yes, sir.
And you know what is this going to be? It is kBT square. You know that ln to the 3/2 means 3/2 will come out, no? And you take a derivative of ln t with respect to t, you get 1/t. What is the answer?
T KBT by 2.
Do you expect this? Is it correct?
Yes.
From your prior physical chemistry knowledge, yes, has to be, because this is nothing but equipartition theorem. You have 3 direction, each direction contributes half kBt, so you have 3/2 kBt. Then for the big system, your partition function is given by n. Okay, q trans to the power of n. Now in that case, this is equal to your whatever the I got. Essentially you get something like v to the power of n and then twice by and then if I calculate average E, can anyone tell me what is the answer? It's very easy.
Tn KBT.
3/2 n kBt.
Yeah, it will have n kBt. And the heat capacity is going to be n kV. Okay, if n is equal to na, Avogadro number, then heat capacity is, you know this, na?
Yes, sir.
Yeah, so you check it. Similarly, single particle level also you can calculate heat capacity. You know that is going to be 3/2 kV, isn't it? 3/2
Yes, sir.
kV. Just put n equal to 1. It doesn't matter what you actually deal with thermodynamic system. The system is huge. Okay, this is fine, going fine. Now let us calculate something else. Let us calculate entropy. What is an expression for entropy? Anybody remembers?
KB log Q plus E bar by T.
If we write down in terms of QA, I think that was the expression for, isn't it?
Yes, sir.
Entropy. So now you know what is Q. Q is given by this expression. So if I follow this expression, let us then write down the expression for entropy. entropy is going to be then, you know this, if I take this, it is essentially kb ln. Let me write this way. Isn't it? And this one is going to be n kb ln q trans. What is the next term?
NKVT DDT of log Q trans.
nkvt. Now you know ddt of ln q trans. You already know this, no? What is this?
3 KVT by 2.
nkvt. You'll get 3 by 2 into 1 by t. So eventually you'll have n kbt kb ln q trans plus 3 by 2 n kb. So this is your expression for entropy. So explicitly if you write entropy, it is going to be n kb ln, you know, or ln, and you know the expression for ln, it is twice by q trans, you know, 3 by 2 into v. Now you see you have also have plus 3 by 2 n kb, isn't it? Now 3 by 2 n kb is what?
CV.
No, that you know, but you can, it is n kb times 3 by 2, no?
Yes, sir.
It is n kb times ln of e to the power of 3 by 2. Can I write like this?
Yes, sir.
So if I write like this, what I'm going to get in the expression? I'm going to get, I can put e here, isn't it? Think is,
Yes, sir.
and then I close it. So this is your expression for entropy. I hope I have not done anything wrong. Just check. I'm sure, I'm hoping that I have not done anything wrong. Okay, it should be fine.
Yes, sir.
Okay, I'll do it. Now I'll further modify this. I'll say this is actually n kb ln v. I take the volume part separate plus n kb ln I can do this, no? Can I do this? I should be able to do this, isn't it? Just because it is ln xy, so I write ln x plus ln y. Okay, because nkb is common. Say yes. Otherwise, I don't
Yes,
know whether you're following. Yes. And this part, so this part, the ln thing, I am calling it sigma. Say, if I call it sigma, then your s is given by n kb ln v plus n kb sigma. Fine. This is one way of writing the thing. Now, what is this sigma? Sigma does not depend on volume. That is important. Huh? It depends on
yes,
temperature. It depends on mass. This is the structure. So now let us go and think of doing an experiment. Okay. Let us go and do the experiment. The experiment is as follows. Okay. The experiment is as follows. where is that? I have a big box, could be a room, and I divide that box or room into two volumes. Both are the same temperature T, and in one volume is V1, other volume is V2. I have n1 number of gas particles in volume V1 and n2 number of gas particles in volume V2. Okay.
Yes, sir.
And these are distinct gas. Molecules or gas molecules. Here actually I'm calling it like atoms, no? This is atomic gas. So how, if you make them distinct, then I can color them if you want. Say I have purple on the left box, and I have, which one you want? Okay, this one on the other box. And then what I do, I remove the partition. What do you expect to happen? What is going to happen?
Mixing of gas molecules.
Yes, the gas molecule will mix, and you'll see something like this. Eventually, you'll see something like this. They will mix, isn't it?
Yes, sir. Mixing. Now, what do you expect in this process? Delta S should be positive. That is you expect, isn't it? Yes, sir.
This is called delta S of mixing. Let us first see whether I get this, starting from statistical mechanical formulation. Okay. So when the partition is on, let us calculate the entropy of the system. So I'll call it initial entropy, SI, in the initial state. Entropy of the initial state. And this is equal to, you know that it's going to be N, rather, I write, it has to be S1 plus S2. Okay, so this has to be N1 kBT ln V1 plus very careful.
Isn't it n kb?
No, it is initial state. No, initial state means S1 is the box 1, S2 is for the box 2.
So T
N1
won't be there, I guess.
Yeah, no, there will be no T. Yes, you're right. Okay. So N1 kb ln V1 into something like sigma 1. Why I'm writing sigma 1?
Because mass is different of the two.
I can have different masses. If you don't want, you can write it. Okay.
In different temperatures.
No, temperature is same. Okay.
Oh, sorry, yes, temperature issue.
This is giving a little trouble. It is sigma 1 N1 kb plus N2 kb ln V2 plus sigma 2 N2 kb. Isn't it? This is initial state.
Yes, sir.
And what is final state? Final state means after removing the partition. If I remove the partition, after removing the partition,
N1 kb log V1 plus V2 plus N2 kb log V1 plus V2.
yeah, it will be N1 because now the gas molecule 1 type 1 can see the total volumes. It is N1 kb ln V1 plus V2 plus you can say N2 kb ln V1 plus V2. Then also you will have N1 sigma 1 plus N2 sigma 2 kb. So what is delta S then? Or delta S of mixing, what you want to call it? It is SF minus SI, isn't it?
Yes, sir.
The sigma part will cancel. What you are left with then?
N1 kb log V1 plus V2 by V1.
Yeah. So let us see. You have this. You have this minus this. This minus. So let me write down first. Okay. Now this V1 plus V2 is total volume. This is V, and N1 plus N2 is total number of molecules, actually atoms here, N. Okay. Now this one you can write it something like this. I can rearrange these things, isn't it? I can rearrange these things. How do I rearrange? I say N1, this term and this term I can combine. N1 kb ln this plus minus this is going to be what? It is ln V by V1. Fine. This one, and this one. Then I do this one and this one. Okay. This one and this one will give you plus N2 kb ln V by V2. This is fine.
Yes, sir.
Now look at carefully. V is greater than V1, V is greater than V2. So the argument of the logarithm is greater than 1. What does it mean?
Positive.
Positive. So essentially it means that the whole quantity is greater than 0. They are convinced, no? Because n's and v's are all positive numbers. Huh? And this condition is maintained. This one.
Yes.
And this one I can just rearrange and write it like this. I just rearrange this and write it as something like minus sometimes yeah, I can write minus n kb into, if I multiply it with minus n, then it has to be n1 by n ln v1 by v plus n2 by n. This is the same thing, I'm just writing like this. Okay. And one can generalize the above expression actually. And this generalization would be something like you have alpha components, one more than two component. This is generalized expression for your mixing entropy. Now I'll do another experiment now. Now I perform the experiment with not distinguishable atomic gases, not one saffron, other purple. It is not like that. Okay. Now I perform with identical or indistinguishable ideal gas. How does it look like? Let us draw the box. Draw the box first. Okay, temperature is same. You have n1 number of atoms and v1 in volume v1, n2 and v2, but they are identical. What does it mean? They have the same color. I cannot distinguish between them. Say which color you want. Say I take pink. And then I maintain a condition that, okay, my condition is that the density of the atoms in the left box is equal to the density of the atom in the right box, and that is equal to the density, total density. So I have this n1 by v1 equal to n2 by v2 equal to n by v. You know what is n? N is and after that, now I remove the partition. And what do you expect now? In terms of entropy. Any answer? Any answer? Hope you are there.
Is it 0?
Actually, you're right. It should be 0. Why it is 0? Can anyone tell me? If anyone can tell me. See, this is because if I now have a situation, let us sometimes it gives me trouble. So idea is as follows. I have to just it is sometimes taking a lot of time. Yes. So it is 0. This is the right answer because even if I remove the partition, I come back and see, I don't see any change in the sense in the arrangement of particles. These particles are indistinguishable and they had the same density before and after. So I don't know whether this particle from the left box has moved to the right box and this one has moved from here to here. They are mixed, no doubt, but the microstates after mixing and before mixing, they are same in number. Number of microstates has not changed. Is this clear? This is possible only when the particles are identical or indistinguishable and you maintain a constant density throughout in both the boxes. Okay, is this clear? So basically this partition is kind of a mental partition. You can think mentally you're putting a partition and then removing, because even after mixing you cannot distinguish. The picture would look identical, isn't it? Because this, first of all, this this partition does not interact with the gas molecules, gas atom. That is an assumption, of course. If that is the case and this partition has no volume, because the volume is constant, v is v1 plus v2, then before the partition and after the partition the entropy should not change because the number of microstates is not changing. Is this clear? This is true only when your particles are indistinguishable and you maintain the same density. Anish, others should also speak.
Can we prove this by substituting
Yes,
N1 by V1 to N2 by V2
that I'm going to do now.
in
The next
the
step.
delta? Okay.
Yeah, so that is the next step. So this is the argument I'm saying. Okay.
Yes, sir.
Okay. I said yes. So let us now calculate delta S mixing. But if I use the same, the one I have used already, I'm going to use the same equation, isn't it? In that equation, I would say give the same value, no? The one I showed, the same expression. This is
S
positive.
final will be different because they are
Yes.
indistinguishable.
Yeah. So one expect this delta S yeah, this giving some trouble. Yes. Okay. So one would expect that delta S yes, delta S 0 should be, but if we use the formula, okay, whatever, huh? Use few minutes back. What is the delta S? And
Positive.
this is called, there's a name for this. This is a paradox. It's called Gibbs paradox. Was it done in any of the courses you had taken earlier?
I don't think so.
This is called Gibbs paradox. Now I'm not going to resolve this paradox. We'll try to resolve this paradox the rest of the class. But my PowerPoint is giving, I think it's too heavy. That's why. I hope you are following the course, because this course is quite intense. You can see, Anish, and number of students attending, it is going down like anything. It is 14 now today. If you don't attend the class, I'm telling you, it is not going to be easy. Okay. And this thing is resolved as follows. Because when the particles are indistinguishable or identical, then I cannot use that formula. I'll tell you what the formula I'm going to use. In that case, your Q is going to be you have to divide by n factorial. Okay. Now, why divide by n factorial? I'll explain this better in the next class. But for this class, take it for granted and that it works. And this is for non-interacting and indistinguishable particles. Or identical particles. Okay. Now let us do this. If I do this way, then what is entropy? Entropy is Kb ln Q plus kbt d ln Q dt t by v. Okay, this is fine.
At constant NV, right?
Sorry, constant n. Yes. This is fine.
Yes, sir.
Yes,
Now,
sir.
yeah. So the entropy is now, I can write it down. I can just I can skip, but it's not a difficult thing to do. But ln q n trans factorial plus kbt ddt of ln. See, the good thing about, again, the second term is that you take derivative with respect to temperature, no? So only the q trans to the power n will contribute, isn't it? You know that?
Yes, sir.
That you have done. That you have done, no? This is going to contribute only that way. So let us do it. This is n kb ln q trans, okay, plus actually, if I say it is minus, actually, you understand that it is minus kb ln n factorial. You understand this, no? If I write like this,
Yes, sir.
plus this is going to be, you can tell me what is this going to be?
3 by
This is
2
again,
nkb.
yeah, I am not going nkb, okay, if you do this. And now I can use starting approximation. If I use starting approximation, I'm going to get nkb, sorry, ln q trans minus nkb, okay, n ln n, no? So n kb ln n plus nkb plus 3 by 2 nkb, isn't it? This is entropy.
Yes, sir.
I can make it slightly bigger. Okay. Now again, I can just rearrange this. You can rearrange this, and if I rearrange this, it's going to be, first let me write down nkb ln, you know what is this? To v, but then you have minus ln n, so it is v by n, no? This is the expression I'm going to use. You can see this expression is different from the one we used a few minutes back. I can further simplify this equation. Okay, I can further simplify this equation, saying, okay, my entropy is, the way I did the last class, S is n kb, you know, ln. I can take ln v common, no? V by n you can take common, no? V by n from the previous expression, and I can take 1e common. 1e I can take it common, okay? And then I can write it like this: nkb ln you understand what I'm doing, no? This is your sigma, old sigma. So what is the structure?
Yes.
Structure is n kb ln ve by n plus n kb sigma. This is another way of writing the same thing. I hope you understood what I've done.
Yes, sir.
Because we had 5 by 2 kbt, no? 5 by 2 nkb, which is 3 by 2 nkb plus nkb. So 1 nkb I have put it here, because nkb is nkb times ln of e, which is this. Then the other part I put it like this. So now I have to use this formula in order to calculate the entropy. So what is the initial entropy then? Initial entropy would be given by, can anyone tell me?
N1 kb log V1 E by N1 plus N1 kb sigma.
E1V plus okay. What is SF? How do you calculate? Actually, you can calculate two ways, isn't it? If you calculate the previous way, you get the same thing. If distinct gas particles, then what will be your way to calculate? Even with this corrected formula, I can calculate the way you have calculated earlier. Any suggestion?
Then we'll get N1 V1 instead of V1 we'll get V1 plus V2 and
Yes.
V2 V1 plus.
So basically, in that case, I'll say, okay, the particles which were in the first box now can go to the whole box, isn't it? So the available volume is V. So I'll write like N1 kb ln instead of V1. What should I write?
V1 plus V2.
Which is V. I don't want to write again and again, isn't it? Total volume.
Yes, sir.
What will the next term? This is okay. And this one is going to be here you assume that particle type 1 has volume V1 plus V2 is equal to V. That is the whole thing, isn't it? Anish, I hope you understand, and others.
Yes,
Then
sir.
what is the delta S mixing? Which is SF minus SI. Can anyone tell me? You can just do the sigma
Same
part.
as
This is not very difficult, no? You will get N1 kb ln
V1 by V2.
by N1 into N1 by V1E plus N2 kb ln V by N2 into N2 by V2E. What is this?
Positive.
Not only positive, it is identical.
Yes, sir.
If I multiply with minus n kb, the way I did, it is N1 by N ln V1 plus V plus N2 by N ln. So we should not be doing this. Even with the corrected formula, if we do this way, then I will get delta S mixing positive. Then what should we do? But particles are identical, no?
Yes, sir.
Then what should be your S final? So correct way of calculating S final is this, as follows. I should write that, okay, the total number of particles, which is N1 plus N2, isn't it? Kb ln E
V
into
by N.
V. V is actually V1 plus V2, which is V, divided by
N1 plus N2.
N2, which is N plus N1 kb sigma 1 plus n2 kb sigma 2. So in this case, what will be the delta S mixing? Let us calculate delta S mixing. So what I have is your n so basically you have, let me write down Si also. What is SY? Si, go back. This was Si, no? N1 kb ln V1 E by N1. Can anyone tell me what is Si?
N1 kb ln V1 E by N1 plus
N1
N1
kb ln,
V1 E by N1
yes,
plus N1 kb sigma,
sigma 1 actually.
but they're equal here,
Yeah. Even if not
plus
equal, they'll
N2
cancel
kb
actually. Yes.
ln, yes,
N2 kb ln V2 E by N2 plus N1 kb sigma 2. So I can use sigma 1. I can just make them different, but they are here same, so they should put it sigma 1 equal to sigma 2. Okay, I put it here.
yes sir,
So what is then delta S mixing? Delta S mixing is this minus this. So I can write it down. This is going to be, I need just 5 more minutes and I'm done. Delta S mixing is going to be N1 kb ln EV by N into N1 by E V1 plus N2 kb ln E V by N into N2 V2, isn't it? This is the expression.
yes sir,
Now we had assumed that because density is after and before, huh? So what does it mean? Then delta S mix is N1 kb ln V by N into N1 by V1. That is the expression, no?
yes sir,
V by N into N2 by V2. But you know that this is equal to this is, isn't it? Inverse of that, isn't it? So this is 1. This is 1. So ln1 is 0. Okay. What we expect, isn't it? So we'll stop here. And the next class, I will explain why you put n factorial. We'll start from here, there. Okay, I hope you have followed the class. Okay.
yes
And
sir.
I think I'll stop now sharing and stop recording. Thank you.